In this lecture, we will solve the problem 2.43 and 2.44 of Griffith 4th edition Introduction to Electrodynamics. The problem 2.43 is find the capacitance per unit length of two coaxial metal cylindrical tubes of radii A and B as shown in figure 2.53. So this is the figure. Now there are two coaxial cylindrical tube. One is with radius, inner one is with radius A and outer one is with radius B. Now we have to find the capacitance of these two uh, cylinder. Uh, Let us say we have a charge Q at the center, that is at cylinder which is having the radius Q, and its length is L. That is this length of the cylinder is capital L. So this length is capital L. So now we have to find the capacitance of this cylinder. Uh, that is from Coulomb's law integral form, integral E dot dA, surface integral is equal to Q uh, over epsilon naught. So the total charge we have taken as Q, and the area is 2 pi S L. S is we are keep moving from center of the both this liter to some distance. That is we are taking this distance is S, and L is the total length, which is equal to Q by epsilon naught. Now you bring 2 pi S L to the right hand side, then we will get E is equal to Q divided by 2 pi epsilon naught S capital L. So in order to get the potential, uh, uh, which is defined as minus between the limit p to a e dot ti. Ti is the uh, small length element, which is equal to, from this formula, e is equal to, I am taking the all constant outside the integral, that is q divided by 2 pi epsilon naught L. Of course, you have minus here. Then S only the variable. S we are changing 0 to that P. Here, sorry, S we are changing between A to P. So this na- normally the definition is sorry, plus infinite to A. We have to take longer distance as a lower limit and lower distance as upper limit. So this will be from P to A. Integrate from P to A, Ts over S. So now V is equal to minus Q over 2 pi epsilon naught L integrated between P to A, Ts over S. So if you integrate 1 over S, you will get natural logarithm of S between the limit P to A. So now if you apply the limit, you will get natural logarithm of A by P. If you interchange the invert this parameter p by a, then this minus will become plus. So now what I'm going to do is, in order to find the potential, we need C is equal to Q by V. You bring V to right hand side, all other thing to the left hand side. Then this will become 2 pi epsilon naught L over natural logarithm of P by A. So in order to find the capacitance per unit length, you divide it by L. That is, you bring L to the left hand side. So C by L is equal to 2 pi epsilon naught divided by natural logarithm of P by A. This is the value for the capacitance per unit length. Then we will move on to the next problem. Next problem is problem 2.44. Suppose the plates of parallel plate capacitor moves closer together by an infinitesimal distance epsilon. As a result of their mutual attraction, uh, this problem contains two parts. See, it is moving by a very small distance epsilon. Then use the equation 2.52 to express the work done by the electrostatic force in terms of field and area of the plate A. Uh, we have to use the equation 2.52. Equation 2.52 is equal to the pressure is equal to epsilon naught divided by 2 E squared. Then the work done is equal to, we know, force into distance. Force can be written as pressure into area, so pressure into area distance. Now pressure we have taken as epsilon naught divided by 2 E squared from this. Then area as it is, and the distance moved epsilon. So this is the work done. Then use the equation 2.46 to express energy lost the field in this process. So the energy stored per unit volume is equal to phi toughness and epsilon naught divided by 2 E squared. So now then total energy lost is, you have to multiply this by volume. So area into distance is volume, and the energy is equal to, is given as epsilon naught divided by 2 E squared, that is energy. So this one first term is energy, and decrease in volume. You remember that we are reducing the distance by epsilon. So A into epsilon is volume, or decrease in volume. So this is equal to energy lost. You can compare these two. So it shows that energy lost during this process is equal to work done by the system. Thank you very much for watching my video and supporting me continuously. Thank you very much.